I heard that. They don't wake me up. I know. Because this morning I was like,
welcome to the Solvay Conference on quantum mechanics in Belgium, 1927.
So we're going to start off with the realist of Albert Einstein. If you care to introduce yourself. Good.
Alright, so our name is Albert Einstein. We are currently 48 years old. We were originally from Germany, but we moved to Switzerland to escape Nazi Germany. During my career, I collaborated with Lorenz, and I was influenced by Isaac Newton.
We have disagreed with certain Newtonian mechanics due to laws of the electromagnetic field. We developed the theory of relativity and realized that it extended to gravitational fields as well, which is one of the two pillars of modern physics. The theory of relativity states that the law of physics are invariant in all inertial frames of reference, and that speed of light is the same for all observers regardless of motion. And this was published in our paper called On the Electrodynamics of Moving Bodies. We received the 1921 Nobel Prize 6 years ago in physics for our services to theoretical physics, and especially our discovery of the law of photoelectric effect, which we will now try and draw on the board.
Just introduction.
Oh, when is the speech then?
Okay. Oh, that's
I just like said half my speech right there.
You don't. Oh, it's okay. We're Albert Einstein. We're all good.
That one's going to be a hard one to follow up. Next is Henrik Lorenz.
You don't have to go to the You can just chill here.
Hi, I'm Hendrik Lorenz. I'm currently 74 years old. I'm Dutch, and that is where I studied and now work. I won the 1902 Nobel Prize, or I shared it with my colleague Zeeman for the discovery and the theoretical explanation of the Zeeman effect, which is the effect of splitting a spectral line into several components in a stationary magnetic field. And then I've also supported the work of Einstein by deriving the transformation equations, which were used in Einstein's theory of special relativity. The transformation equations are a family of linear transformations from a coordinate frame in space-time to another frame at a constant velocity. Yeah, that's all.
Thanks, Henry. Next is Luis de Broglie.
So I'm Prince Louis de Broglie. I'm originally from France. I'm from nobility. So I went to since I'm from nobility, I was granted lots of lots of privileges and classes, and also I served in the Great War. Back then, I served in the Great War, so you all owe me. So I developed my theory on particle waves, like particles don't only move in, like electrons don't only move in particles, but they actually move in waves, like in a, like there's a internal clock, so everything's in a realistic motion. It's not in a, everything's not like random. It has a certain motion to it, so it's in a wave, not in a, and so they both move in waves and not particles, stuff like that.
Next up is Erwin Schrodinger.
I'm Erwin Schrodinger. I'm from Vienna, Austria. I'm 40 years old. I served in the Great War as an artillery officer for the Italians. I studied not the conventional for physics, but I also studied Eastern mysticism and was influenced by philosophy. I actually was just appointed to replace Max Planck at Friedrich Wilhelm University in Berlin, and I've held positions in academia in Poland, Germany, and Switzerland.
Next is Max Planck.
Hey everyone, we're Max Planck. We're 69 years old, born in Kiel, Germany, to Emma Planck and Julius Wilhelm, who was a professor of law. We studied at the universities of Berlin and Munich and received our doctorate in philosophy. And last year we recently just retired from Berlin University, but were appointed to the president of Kaiser Wilhelm Society for the promotion of science. And our first impactful studies succeeded the research of the famous German physicist Gustav Kirchhoff and his work with thermodynamics, which would become what we became most famous for. And our studies in 1900 on thermodynamics ended up winning us the Nobel Prize for Physics in 1918. And I've studied alongside a lot of my colleagues such as Einstein, Bohr, and our protege Schrodinger over here. So thank you.
Next is Werner Heisenberg.
So we are the Werner Heisenberg. We're a German physicist. We got our PhD in 1923 and we spent a lot of time in Copenhagen working with Bohr, where we developed some uncertainty principle. Then we're also very known for a theory of quantum mechanics, but use the form of mathematics that few of our colleagues understand.
Yeah, so we're most known for the uncertainty principle and also the neutron-proton model of the nucleus. And we studied at the University of Munich and got our PhD in 1920.
Niels Bohr.
Hi, we're Niels Bohr. We're currently 42 years old. We were born in October of 1885 in Copenhagen, Denmark, and we also studied there as well. Some of our collaborators at the conference are Heisenberg, and we spearheaded the conference with Albert Einstein over an argument of differences in quantum mechanics, and we are the head of the group. Some of our famous discoveries include that our initial thought was that the electron was able to occupy only certain orbits around the nucleus, and we were actually the first person to create the first model to use the quantum theory. Our model proved that when jumping from orbit to orbit with lower energy, a light quantum is emitted, also in the form of a wave. We also believed in the principle of observation, which causes the wave to collapse along with the double slit model. And we won the 1922 Nobel Prize for the structure of the hydrogen atom.
Next is Wolfgang Pauli.
So our name is Wolfgang Pauli. We're from Austria. We attended the Ludwig Maximilians University in Munich, where we worked under my mentor Arnold Sommerfeld, a theoretical physicist. I earned my PhD at 21 on the quantum theory of ionized diatomic hydrogen. I'm one of the youngest people invited to the conference, and I played a large role in developing theory on quantum mechanics, Bohr's atomic theory, and the exclusion principle. However, I believe that physics should only deal with the real things that can be observed.
Yeah, like I said, we're really young, we're 27 years old, we like to drink hard liquor and womanize. We're fresh out of school, and yeah, we're very And then we're really well known for the relativistic theory of spin by this matrices that we developed. And our kind of go-to insult for our students, because we're a lecturer as well at the University of Hamburg, is we like to tell them that their assertion was so bad that it's not even wrong because you can't prove it wrong.
Next up is Max Bourne.
I'm Max Bourne. I was born in Breslau when it was a part of Germany though. Now it's in Poland because there's a whole treaty. My schooling included time spent at König Wilhelms Gymnasium in Breslau, and it continued at the University of Breslau. I have my PhD from the University of Göttingen, and I also studied in Cambridge for a short period of time where I explored the theory of relativity. And then in 1915, I was offered a position working with Max Planck at Berlin University, but the war had just begun, and I had to join the armed forces, where I worked on the theory of sound ranging.
Okay, it was around this time that I published my first book, The Dynamics of Crystal Lattice Structure. After the war and a brief time at the University of Frankfurt am Main, I ended up as a professor at the University of Göttingen in 1921, and I have remained there since, where I have spent much of my time working with other attendees of this conference, Wolfgang Pauli, Paul Dirac. 2 years ago, I worked alongside Werner Heisenberg to formulate the matrix mechanics form of quantum mechanics. I also worked to develop the understanding that the square of the wave function in Schrödinger's equation represented the probability distribution of electrons in space around an atom.
Next is Paul A.M. Dirac.
What's up? We're Paul Dirac, 25-year-old English theoretical physicist, and I contributed to early quantum mechanics and quantum electrodynamics. I was educated at the University of Bristol and got my PhD last year from Cambridge.
We studied under Ralph Fowler and worked on the statistical mechanics of white dwarf stars, and completed my PhD in 1926 with that thesis. Fun fact about me, I like to go on strolls on Sunday, and I just finished a paper called The Quantum Theory of the Emission and Absorption of Radiation.
Alright, Marie Curie.
Hi, Marie Curie. I was born in Poland in 1867, so I'm currently 6 years old. I lived in Poland for a bit, but then I moved to Paris after I met my husband, Pierre. And along with him and Henry Becquerel, we won the Nobel Prize in 1903. I was the first woman to win the Nobel Prize. And then in 1911, I won a second Nobel Prize for my study of radium and polynomium. And I was the first person to win 2 Nobel Prizes. I'm most known for my discovery of radioactivity with my husband and Henry Becquerel.
Next up is us, Paul Ehrenfest.
We're Paul Ehrenfest. We were born on January 18th, 1880. I was 47 years old. An Austrian theoretical physicist who made major contributions to the field of statistical mechanics and its relatives with quantum mechanics, including the theory of phase transition and the Ehrenfest theorem. I studied at with Ludwig Boltzmann at the University of Vienna, where he received his doctorate in 1904. And we're a very close friend of both Albert Einstein and Niels Bohr. And we're sad that they've developed such a strong opposition to each other.
Next is William Lawrence Bragg.
Hi, we're William Lawrence Bragg. We're 37 years old and a physicist and an X-ray crystallographer from Australia. We attended 3 universities and have biggest collaborator is our father, William Henry Bragg, who's a physics professor, and together we won the Nobel Prize for Physics in 1915, making us the youngest person ever to win this award. And together, us and our father have published lots of papers about the atomic structure of minerals and crystals.
We also established the relationship between the wavelength of the X-ray, its angle of incidence, and the distance between the atomic particles and the crystal. And that lets people examine crystals today in different ways.
Arthur H. Compton.
Hi, we're Arthur Compton. We're 35 from Ohio. We obtained our PhD at Princeton University studying X-ray reflection, and we worked as a professor and spent 2 years at Westinghouse where we helped develop the study and paper lab. After 2 years at Cambridge University, we became head of the physics department at Washington University in St. Louis, Missouri.
And we received the Nobel Prize for, this year from our 1923 discovery of the Compton effect, demonstrating the particle nature of electromagnetic radiation.
Next is Leo Brion.
I am Elon Brion. I am a French physicist. I was born in Paris in 1889. I'm currently 38 years old. I received a PhD at the University of Paris under the supervision of Marie Curie, Paul Langevin, and Jean Perrin. My thesis involved application of quantum mechanics to solids, and I currently work as a scientific secretary for the Journal de Physique at the Rady.
Alright, so now we'll move on to our 5-minute speeches. First up is Marie Curie, the forms of radioactivity. Start off hot.
So like I mentioned, I'm just gonna write the so how I came to discover these elements, that's just how I spell them. I was fascinated with Henry Becquerel's study that uranium casts of rays weaken, are weaker than X-rays. So I decided to take that study further, and I found that uranium rays actually stay constant no matter the condition or form, and found that the rays actually come from the atomic structure, which led to my creation of the field of atomic physics, which I coined radioactivity, which is defined as the activity of rays to be dependent on uranium's atomic structure. So using the mineral pitch blend, I found the two radioactive elements, polonium and uranium. I named polonium after my home country, Poland, and then I later found radium. Radioactivity for you.
Alright, so now we got Max Planck. Yeah. You got Max.
Alright, how's it going, everyone? So like you said, we're Max Planck, and our studies were based around blackbody radiation and Planck's constant, which we'll get into. So first, to talk about blackbody radiation, I think it's easiest to understand what the two words mean. So as Marie Curie said, radiation is it's any form of energy emitted by electromagnetic waves that's given off by all objects that have a temperature above absolute zero. So basically it's just like a form of energy that all objects give off. And then black body is basically like a theoretical, completely black body. of any like shape or form, so it's gonna absorb all light and all radiation that's on it. And so in just before 1900, there was an experiment done with a black box. And it had one little hole on top, so the box was completely black, or as close to possible, completely black as they could get. And this experiment was done by Lord Rayleigh and James John, and they were trying to find out how radiation would emit thermal energy. And they found that while using classic mechanics, they found as the frequency of the light increased, the thermal energy emitted also continually increased, and it could be at any given point. So they were partly true in that the box will emit electromagnetic radiation, but they were incorrect with their assumption that increasing wavelength is going to increase energy forever. So they needed to assume the existence of energy quanta, which you may know as photons, or that are basically just pockets of energy found inside light particles. So that's what I did. I came up with that. And I found that there was a maximum amount of thermal energy that could be produced radiating from a black body. And I also found that temperature was the only factor determining the energy produced at any given wavelength. So basically, they came up with the equation. It's wavelength equals temperature times Wien's constant, who was another scientist. He came up with this equation, and I was the one who found out that it was temperature that was the only limiting factor. But I also was able to redefine this equation to be more accurate, and that gave us a massive equation, which is, copy it down. So basically what this equation says is the spectral radiance of an object, like how much light it's giving off, is going to be equal to this number here, which this V is the wavelength, this H is my constant, Planck's constant, which I'll talk about, and this is the speed of light squared. And then this is going to be Boltzmann's constant, which was invented by Ludwig Boltzmann, an Austrian physicist. So that was the equation that I became most famous for. But basically what this says is very simple. It can be broken down to this equation, which says one main thing, and it's my biggest finding, was that the energy is equal to any given number times h, Planck's constant, times wavelength, v. And basically what that's going to say is that what this first experiment found by Jean and Rayleigh was that the energy level produced could be at any given point, whereas I found that they have to be at a specific number of levels based on their frequency and wavelength. And that's because all the energy is carried in the photons of light, or energy quanta as we call it. So those are my findings. Thank you.
Alright, next up we got Albert Einstein.
Einstein combated some of the laws of Newtonian mechanics due to the laws of the electromagnetic field, which then proceeded into him developing the theory of relativity, which states that the law of physics are invariant in all inertial frames of reference, and that the speed of light is the same equals mc squared, where E is energy and mc is the speed of light squared. We received the Nobel Prize 6 years ago in physics for services to theoretical physics, and especially our discovery of the law of the photoelectric effect, which is essentially described as the emission of electrons or other free carriers when light hits a certain material. And according to electromagnetic theory, the photoelectric effect can be attributed to the transfer of energy from the light to an electron. From this perspective, an alteration in any intensity of the light itself induces a change in the actual kinetic energy of the electrons. And all of that can be explained in the paper on the electrodynamics of moving bodies. And that's the example of the electric effect. Yeah.
Next up, we got Niels Bohr.
Yeah.
Yeah, Neil.
Okay. So in terms of our famous discoveries, like we talked about before, we discovered the Bohr model of the atom, and that was basically based on our assumption that Rutherford's findings were wrong. So we felt that the electron was able to occupy only certain orbits around the nucleus, whereas Rutherford kind of assumed that his motions of electrons were not as stable. We did this by using the constant as well because we wanted to search for an accurate theory for the atom, and it used dimensions that combined the mass and the charge of the electron to produce a measure of length. And we felt that the energy of the electron in this case also depended on its size. So how we came about with our model. So the first model of the atom was actually represented by this in 1803 by John Dalton. And since then, it's been proven that the true nature of the proton and neutron. So initially, they thought that atoms just composed of protons, neutrons, and electrons kind of just floating around. And so then Rutherford's demonstration of the model proved that there was a nucleus with protons and neutrons, but he only had one orbit for the electrons that went around in a circle. But the problem with that is, if all of the electrons were to go in a constant orbit, they would produce electromagnetic energy and thereby give off energy and lose energy, which would make them fall into the nucleus and the atom would become completely unstable, which is where our model came in. So our model proposes that the electrons are still in orbit, but with shells that have definitive energy, which is represented by 2n squared. So the first shell of any atom can hold 2 electrons, and then from there, every other shell can hold up to 8 electrons. So for example, carbon, how this works is you take the atomic number of whatever the material is, and that's the amount of protons that there are. So for carbon, there are 6 protons. To find the neutrons, you take the atomic weight, which for carbon is 12.011, and you round it to the nearest whole number, which is 12, and then subtract it from the amount of protons there are, which means that there are 6 neutrons. And then in our example, this is going to be a stable atom, so that means that the protons are going to be equal to the electrons. So for the first shell, there are 2 electrons, and then for the second shell, there's going to be 4 electrons that are in stable orbit, and that's our model.
So next up we have Leon.
So I'm gonna talk about the double slit experiment. And what this shows is the duality, or the particle duality. So in this experiment, they shot electrons up a wall that looks like this. There's two slits in it, and you'd think that on the other side it would come up on the wall that it would look like this. But what they found was it actually looked something like this. And that is because when the electrons went through, so imagine this is the top view of the two slits. The waves, they look like this. They create waves. And this one created waves. And at like points like this, that's where these the particles came up on the wall on the back and created these patterns. So they were most thick in the center, and then got weaker and weaker as they went out to the edge. But when they observed it, they found out that the electron went straight through it and hit the wall, something similar like that. So this just shows that the particles like sometimes act like waves and act like a particle moving. So yeah.
Next is Luis de Brogley.
Okay, so you want me to interrupt it? So we're talking about the de Broglie wave, which is basically our idea that all matter acts as waves. The atomic particles, sort of like we were talking about the double slit experiment, behave like photons, which like Beyond was just talking about how the waves cancel out. So the de Broglie wavelength is an equation that I came up with, which is basically determining the wavelength of these waves when a particle is moving. And it's calculated as Planck's constant, identified as h, divided by the momentum, which is mass times velocity.
So the waves. So basically, it's basically like the slit, but it's also but in a different way because like you go. So like at first, what people used to think was that when particles like went through when particles went through it came out. It would come out like. It wouldn't come out like it would just come out when electrons went through. They'll only come out particles, but what we saw was that when electrons actually go through, they don't come out like this, but they more come out like that. So they more come out like waves instead of particles. So it's more, but in a different sort of way that like it somehow in a way it also came out as both because they like from a different angle you could actually see that the waves became particles, but the particles also became waves, and that like from different angles. Like at first, like looking straight through it, you could see it's just waves, but when you look from a different angle, it just becomes particles. So it determines that it is.
Basically determining that there's wave-particle duality, and that sort of like we examined the other day, that when you observe the individual slit, it seems like the particles are going straight through it, but when you observe the entire wall as a whole, you can see the waves that when they go through both slits, like we were talking about, how it goes through like a wave and not random.
I didn't really do this. This is a theoretical experiment that I came up with. Here's a box. You put a cat in it. Let's make it, you know, put some little whiskers on that. And then you put poison in this box with a little hammer above it. And a Geiger counter as well. So if that box, if the Geiger counter picks up this amount of poison in the air, it will drop the hammer and break that vase or whatever that it is that contains the poison. Does this mean the cat is, if we have this box closed, do we know if the cat is dead or alive? Or you could take a superposition, that means that the cat is both dead and alive at the same time. I do not believe that, because if one cannot be in the zombie-like state of both being dead and alive at the same time. Through observation, you're not killing the cat though, but you are just finding out the result. No matter what, the cat was either already dead or it was still alive, based off of 50-50 chance, depending on if the Geiger counter picked up the box, or picked up the poison and the hammer dropped and killed it. So some people will say that the superposition state of that the observation is what kills the cat, but that is simply not true, because observation does not already increase what the fact has already been. The cat was either already dead or alive at the same time. Dead or alive, one cannot be in both states at the same amount of time. So again, when you open it, you will determine the fact of the science that it was either dead or alive, based off that.
Alright, so that concludes our speeches. So now we're going to open it up for the debate. So I'll pose the first question. Is the universe fundamentally random or predictable? Anyone? Yeah. So I guess raise your hands if you think it's random. And then raise your hand if you think it's predictable. Looks pretty evenly split.
You need to argue it.
Yeah, I was about to say, does anyone have any explanation or reason behind why they think that?
I'll start. God doesn't roll dice. He predetermines it all. You can determine it all with science. God doesn't roll dice, so why would we have to deal with that?
Religion is simply a way to keep people in society quiet. So that there is no God that is needed to roll the dice. That's direct. We believe that the world is random and like you just gotta take chances.
Yeah, ultimately your entire view of the universe is one of random events made real by being observed. So it's not really real, it's random. Yeah, I can also say that developing a philosophical position based on just single events is silly. The universe is an ensemble of many events combined.
I would also like to add, I found out, Max Planck here, found out that energy is not just like random throughout the air, it's like contained in small quanta energy, so it's, I mean, that proves that like everything can be contained within something, it's not just all floating around at random.
Any other thoughts?
I also think that we should be able to describe physical phenomenon in images, be able to see it in distinct images, and that even though it may seem that electrons appear to behave randomly, we also need to understand that there's a deterministic causal process that works that is making these seemingly random events happen, and that if we just look hard enough, we can actually determine these patterns or events that occur naturally that aren't random that make these scenery movements happen.
As my colleague said, theory is not really important, and with electrons, you shouldn't care about trying to ascertain the actual orbits of electrons because they can't be visually observed. We can only worry about the changes that can be observed with their energy.
As for finding a pattern or anything to make it not random, if you look at anything long enough, you can find a pattern in it. But the ultimate reality is it's random. It's based off random probability.
You have you wanna reply to that or?
Well, I think that, like for example, you may see an electron as something that exists at a point in time and space, and if it reappears somewhere else, it had to have some trajectory from one place to another to get there. It couldn't have just randomly appeared there. There has to be an explanation. And I think though that's a basic explanation, that can be expanded into more advanced, complex concepts, and using the correct scientific process, you can then extract how you got from point A to point B using a pattern or a specific set thing.
I'm a pretty good scientist and I haven't seen that yet, so.
Alright, I think we could stop there with that one. Just a quick question for you. Do you want us to re-vote now or at the end?
We do.
At the end, okay. So I'll pose a second question. Can something be both a particle and a wave at the same time? If anyone has any thoughts or comments on that?
Can you repeat the question?
Can something be both a particle and a wave at the same time?
Would you like to explain why you think that?
Sure. So I'm very, if a photon, like if you break something down to the photon level, and you put it through, like the double slit experiment, when it goes through a slit and it strikes the screen, it's acting as a wave. But if it's observed going through the slit, it can be a wave function.
Also, going off of that, we kind of use it as a way of saying like it's collapsing into one. So when they collapse, both the wave turns into a single value before the slit, and it's actually observed as a particle. And that's how we kind of interpreted the double slit experiment.
Yeah, because like you said, it's based off what you actually observe. So if you observe it striking the screen, it'll act as a wave. If you observe it going through the slit, it acts as a particle.
Why does it matter, Heisenberg, if you observe it or not?
Because, like I said in the beginning, if you were paying attention, your entire view of the universe is one of random effects made real by being observed.
Einstein?
Well, in terms of the double slit experiment, we can't actually observe a single photon going through the apparatus. What we observe is a result of sending an ensemble of identically compared photons through one at a time. So the diffraction pattern is an assembled property, not the property of random chance or a single photon.
If no one has any more comments, we can move on to the third one. Wasn't great to take Alright. Third question. Is an observer required to kill Schrodinger's cat? Schrodinger.
Absolutely not. The cat is either dead or alive. We find the answer to if it was breathing or not at the end.
De Brogley here. So going along with Schrodinger, I mean, the cat is alive until it dies. I mean, you don't have to observe that to sort of understand that.
I mean, try that in a court floor. Try that in a court floor. I tied the woman on the train tracks and I left. I didn't kill her because I didn't observe it.
Facts.
Don't mess with cats.
Yeah.
Clearly, we can see from the double slit experiment that they're, like, having an observer does change something's outcome. So the observer can have, being an observer, existing as an observer and seeing the result has an effect. So it would have an effect on Schrodinger's cat as well.
But if the glass broke, how did it not? It was already dead. Like if the glass breaks, it's dead. Even if it's not, even if we can't, it's like asking if a tree falls in the wood and nobody's around and it made a sound.
Exactly what it is.
It made a sound. It made a sound. You can't say it didn't make a sound.
But how can you make a say? Actually, never mind.
You're on my side. That's the.
Heisenberg, you got something to say?
Like believing in Santa Claus, like you don't see it, so how do you know how?
So,
Sorry.
What's we doing in God? How do you think?
what the fuck?
So to sort of combat the double slit experiment argument, the electrons don't have like the physical choice. Like the cat can break the glass on its own accord, or it could choose to not. But the particles going through, they have a set pattern, like we were talking about with question 2. They have a set pattern that they go through scientifically once they go through the slit. The cat can choose to break the glass or not based on its own accord, or do it by accident. So it doesn't really have, cat has more control.
Going off that, you want Alright, now we'll vote, I guess, so we'll go back to the first one. So is the universe fundamentally random or predictable? So
Everyone has to vote.
So we'll do for raise your hand if you think random. Want a good count over there, maybe? Show me a nail biter. Alright, and then raise your hand for predictable. Predictable one. Alright, so can something be both a particle and a wave at the same time? So raise your hand if you think it can be a particle and a wave at the same time. Alright, and then raise your hand if you think it can't. Alright, and then finally, is an observer required to kill Schrodinger's cat? Raise your hand if you think yes. Kill it. Alright, and then raise your hand if you think they aren't required. Alright, if they aren't required, take that one. Alright, now that concludes our debate.
Thanks for test driving that as a game. There's a series of published games that are usually done in the humanities and history. Some of you have played those. There are some that are done in the sciences. And honestly, in terms of doing a quantum mechanics game, I didn't think that was a necessarily good idea, but then this colleague of mine, David Henderson, put this together as a draft and said, hey, this is tryable. I took that and sort of cut out some of the pieces because he had more complex to say which pieces might play out in either the beginning of a physics majors class or the end of a class for non-majors. It seems like the Schrodinger's cat question is one you played into a little bit more than the others. Is that a fair interpretation?
Yeah.
what are the pieces that you saw that that were more interesting or less interesting?
It was just kind of easier to understand from somebody, especially in the J-term class where you only have 3 weeks of class.
Yeah.
It's just as simple as, does an observation kill it? Like,
Yeah.
that simplicity was easier for us all to like formulate an opinion based on one person.
Right. Yeah.
I also feel like people are just familiar with the shrimp juice cat experience. The other ones probably not as much.
And that was one of the things, the original game that he had, since it didn't exist, I'm sure he had formulated that at the time of the conference, that it wasn't in the original game, and I've added it, but I actually think it needs to be slightly more infused into it, sort of to drive the discussion. And so, sort of having watched you, I think the next edit of it that they do next year, that'll happen earlier, and or they'll jump into the questions earlier for it. But yeah, thanks for playing that. That's not a polished game. It's sort of hard. It's easier to have one of these role-playing scenarios about something that happened in history, like the 1968 convention, or protest movements, or the trial of Galileo. It's harder to do it for quantum mechanics. But I think sort of bring in real characters. How many people learned something by looking at your characters? Like, which characters did you think were more interesting than not? And what would you find interesting about your character? Yeah, anyway, anybody.
My dad won the Nobel Peace Prize at 25.
Oh, okay.
Nobel Prize.
Nobel Prize. Yeah, how many people had a character that won the Nobel Prize? Because it's ridiculous that there are that many people that either had won it or would win it at this one time in history, which is why Henderson wanted to write this as a game, because it's just such a weird moment when some of the smartest people of that decade all happen to be one time. Yeah.
I thought it was interesting, like, the attributes that, like, people have. Like, my character was very, like, quiet, and it said that, like, he didn't really talk to many people.
Yeah.
Like, one of the funny stories I read was he'd only say, like, a word every hour. So in college, we call him Dirac. Like, that was the term for a word an hour.
Oh, yeah.
So I thought it was funny, just like how people
Yeah, and there's a lot of interesting little biographical stuff that came out in a book called The Quantum 10, which just focuses on 10 of those.
It was also like really interesting to learn about like who they collaborated with, as well as like for us, like we were in Neural's work. It was like really interesting to learn about like how his whole like thought process and like research process worked with him like developing his own form of the.
And that's something that gets downplayed in a lot of science, or in Science 101, is that a lot of science is driven by who are the friends of the scientists. Like your ideas as to what the answer is driven by what did you learn when you were a student, who was your mentor, and who are your friends with. And I didn't do that with quantum, but the big question when I was in graduate school was, what are gamma ray bursts? And there are 2 camps. There was the Alabama crew, and there was the Chicago crew. And I was working for somebody who was friends with the Chicago crew, so yeah, they must be right. And there was a decade or more of those teams, the Huntsville, Alabama crew versus the Chicago crew, going and debating this, and finally a piece of evidence comes along in the mid or late 90s, and it's like, oh wait, no, Alabama was right. That was it. Like people quit arguing it at that point. But for years, with the data being up in the air, you take what flimsy data you have and couple that with like who do you trust, and then that comes in. So the fact that they were friends and acquaintances, and had shaped their beliefs to some extent. All right, thanks again for trying this. Do you have other pieces about the game that you want to share? Did you have other aspects about the game that you want to share with them? Cool. All right, thanks again for letting me trying this out for us.